Good evening. I'd like to welcome Steve Webb back. Steve runs Webb Yates, fantastically talented structural engineer, of which there's a great history of in this country, and Steve carries on with that great tradition. Super inventive and also a great advocate of using materials like stone, for instance, as a structural material in a way that hasn't really been used. It hasn't really been used for sort of centuries. So, re-looking at that, which is quite radical, as you will see. So, thanks so much for coming back. Thanks for working with Maria's studio. I know they appreciate it. So, yeah, it was great to have you. Thank you. Cheers.
Do you want to come forward? Maybe. Yeah, come to the front. You know, come on. This is like I could probably take the microphone off as well. Well, you don't have to. Oh, is the clicker? Do you know where the clicker? Oh, is that it? Yeah. Is it on?
Where is everybody? Sit at the front, guys. And I got the shot.
Can I get a refill of the thing? Yeah, the whole bowl. Yeah. Ooh. This is not the presentation I was expecting. Okay. What is the social context of the way that we build buildings and the decisions that we make when we're building buildings? So I'm an engineer. I'm from Webb Yates Engineers. We're structural, civil, and MEP. 65 of us who work in London and Birmingham. We do projects all over the world. And I started off working as a tunneling engineer many, many years ago, maybe 30 years ago on the Jubilee Line extension, and I worked for Calatrava in Spain and engineers in London. Started our practice 20 years ago from nothing. So I came back from working for Calatrava thinking that the world would fall at my feet and we would get hundreds of massive projects, but actually we got nothing but back extensions and loft conversions for quite a long time. But we're a bigger practice now, we do bigger work. And we've always been interested in sustainability and carbon and the ethics of what we're doing. So the question about social context for an engineer is something that we find quite interesting. Why do we do things the way that we do them? And it's a question that extends from engineers, more importantly, to architects and contractors and to other people as well. So speaking as an engineer, we quite like it when our buildings don't fall down. That's kind of the primary reason. And actually, when I'm talking to engineers teaching at some of the universities of engineers, they're very obsessed with factors of safety and calculations and the safety aspects of engineering. But actually, I would say that's kind of entry level. You know, that's the minimum that you would expect of an engineer. And possibly why, in many places, that's the only reason that you hire an engineer. The second reason is probably economy. You don't want to make things bigger than they have to be. You want to make things economical. Put the minimum amount of structure in the building to make it stand up so that people can afford more buildings or make more profit. An emancipated engineer, which I thought was a great term, implying that engineers are slaves to architects in some way. An emancipated or imaginative engineer, we like to make the structure part of the architecture. We want to make the structure really interesting so that you're not tempted to cover it in plasterboard and cheesy metal cladding and whatever other finishes you want to slap all over it. So structure can be beautiful, can be logical and beautiful. There's no what would you say, mutual exclusivity between a structure being beautiful and being safe and standing up. We're really interested in what kind of work we create when we choose how to build a building. So if you decide to make a building out of concrete, who are you making work for? You're making work for a cement factory, making work for a batching plant. You're making work for mechanized processes. Similar to steel, if you decide to build a building out of steel, you're giving work to a blast furnace, you're giving work to a rolling mill, and you're sending money to capital, which is, I think, an interesting politicization of the decisions that you make. If you choose to make a timber building, maybe you're making work for carpenters, or maybe you're making a more distributed, more social kind of work for people to do. Similarly, the relationship between the cost of labor and the cost of material has a massive impact in the way that we build. So if labor is very expensive and material is quite cheap, then what we tend to do is over-rationalize structures. So we build big flat concrete slabs that are very easy and quick to build, very quick to design, less work for the engineer, less work for the form worker, less work for people in general, more work for mechanized processes. So if you have labor expensive, materials cheap, and bad for the environment because you'll use a lot more material in order to avoid having labor. That isn't always the case. So this is Luigi Nervi in Rome. After the Second World War, there was a shortage of coal, and material became very expensive relative to labor. And so in this building, you can see that they've gone to huge lengths to save concrete. And there's a whole crop of buildings from this period. Eladio d'Este in the south, in Uruguay, Felix Candela, Torroja in Spain, where they're trying to minimize material use, but they're able to put a lot of money into formwork and false work and other things like that. And the thing that possibly affects that is income tax. So tax really distorts the relationships and the decisions that we make in building. William Pitt the Younger, who I think on the back of the window tax, has anyone heard of the window tax? So the window tax, they were taxing people per window and they were bricking up all the windows. The next great tax idea they came up with was income tax. Actually to raise money to fight the Napoleonic Wars, but income tax obviously make labor more expensive. So we pay 30 or 40% more for labor than we pay for materials. Materials aren't really taxed. So the taxation actually creates an environment where we have over-rationalized structures that consume a lot more carbon and consume a lot more material. If we move the tax from the people to the material, suddenly this is the kind of architecture we would have. They would be paying all of us a lot more money. People will be spending a lot more time, a lot more form work, a lot more shuttering, a lot more careful use of material, less carbon, less environmental damage. Who likes CNC? You guys are lots of robots, right, downstairs? So is this the future that you imagine from CNC? I'm kind of so I think I'm a Luddite. Do you know what a Luddite is? So when they first introduced the cotton mills or mechanized weaving of cotton, there were a whole series of traditional weavers, or traditional weavers, who were very concerned about their jobs and protecting their jobs, and they smashed the machines, and they were the Luddites. And they were against the adoption of technology in industry, but economists would argue against this. They were saying, actually, their labor is freed up to do something more productive. So you can mechanize things, you can release the labor, you can do something more productive, you can increase productivity, which in 1800, when people really had very little and consumed very little, was probably a great idea. But at the moment where consumption is actually a problem, do we really want to release people from work to be more productive? Like, do we really want to produce more in order to consume more? Is this good for us? Or do we want to occupy people in jobs that they're happy with, producing enough and not too much? So the question of CNC is it going to be this? Actually, all the people who are doing those jobs are probably going to end up on universal income. What are they going to be doing? So those sorts of questions, when we're deciding what materials we use to build a building, are very important. The biggest challenge, so the guys in my office were saying that they wanted to join the climate change march in Trafalgar Square, and they're saying there's a big march, we want to go and join the march. And it's like, oh, who are they protesting against? Oh, it's all about carbon. Like, yeah, what? What about carbon? Oh, industry producing a lot of carbon, we want to go and protest against it. Then what industries produce a lot of carbon? Well, steel manufacturing, concrete manufacturing. Well, who's specifying all that stuff? Oh, we are. why don't you go down Trafalgar Square and protest against yourselves? We're saying, well, it'd be better to stay in the office for a few hours and design a timber building, change your steel building to a timber building, take a few of those steels out and make it out of wood. There are lots of ways of evaluating carbon in buildings. It's really complicated. There are a myriad of spreadsheets, and I think the complexity of it and the tendency of people to adopt acronyms, REBA 2030, LETI this, LETI that, all very complicated, falls off the end of my attention span, I have to say. It's very simple. If the material you're using has a great big fire at its origin, it's a high carbon material. If it doesn't have a great big fire at its point of origin, it's probably not a high carbon material. So here we've got blast furnace, forest, quarry, I don't know what that is, brickworks, something like that. But you can see where the carbon is coming from, and you can make decisions about materials quite easily, in fact. This talk is about stone and a bit about timber, but stone particularly. We, as a society, take 200 Newton pieces of stone, maybe 100 or 200 Newton pieces of stone. We crush it up, we get a load of gas, we burn it to make cement, we get fresh water and sharp sand, both of which are in short supply. We put up formwork, reinforcement, releasing agent, backpropping, we vibrate it, we let it set for 28 days, and afterwards we've got a 40 Newton block of concrete. So we threw the entire inventory of our industrial development and a huge amount of energy converting what was a really competent structural material into a sort of mediocre one. And we have a climate crisis. So you think, is this really a little perverse, perhaps? What are the, in terms of what we build with, what are the differences? So you might say steel is really bad for the environment, but it's very strong, so we don't use very much, whereas we use a lot more timber. This is a comparison of duty for duty elements, structural elements. So it's a 2-meter span beam carrying a 1-ton car. I don't know if I can point with this. Oh, no, I didn't want to do that. Okay, I'll point like this. The top row are all strong enough to carry that weight. So it's a 200 by 100 piece of softwood, thinner pieces of hardwood, 28 millimeter slither of concrete, 2.1 millimeter slither of steel, and a post-tension stone beam at 22 mil. So you would never build with these sections, but they're a kind of pro-rata comparison doing the same thing. Most structural elements are sized for deflection. They're not really sized for strength, so you're more worried about things sagging than falling down. Falling down is often easier than sagging. So all of those sections in the middle are the same stiffness. And on the bottom row is the carbon in kilograms per meter for those sections. So the steel beam, which is only 5.1 millimeters thick, has 22 kilograms per meter, 14 for the concrete, 5 for the timber, minus 16 if you account for sequestration. So sequestration, as you probably all know, is the tree consumes carbon while it's growing. So people like to say that timber is carbon negative. If you drive into a forest in a huge diesel truck and you light up your chainsaw, it's belching smoke, diesel smoke and petrol smoke all over the place. None of those things are carbon negative. Actually, what's carbon negative is the tree regrows afterwards if you replant the tree, which takes probably 30 years to cancel out the carbon that you dug up. So it is carbon negative in the long run if you continually replant the trees, if you plant more trees than you cut down in the first place, but it's not carbon negative today, and actually of those options, it's not the best one. Stone, which is much stronger than timber, and has a similar degree of processing, only has 1.5 kilograms per meter run today. So actually the stone is, in immediate terms, the better option even compared to timber. People have said, well, somebody said to me at a talk, oh, that's all very well. What happens when all the stone is used up? Can you imagine a sort of Saturn's belt of office buildings floating around? We've consumed the entire planet and turned it into buildings. Impossible. We can never use up all the stone. If 7 billion people had a 5 by 5 meter by 200 millimeter thick slab, it's a whole 40 kilometers square, 20 meters deep. So compared to the volume of the Earth's crust, building is nothing. It's a grain of sugar on a beach. So there's plenty of stone. And if you ever got close to consuming all the stone, a lot of new stone will bubble up in its place. And in some ways, it's like harnessing geothermal energy to make a building material rather than some other kind of energy. In comparison to, so it's quite easy to see why it's better than better than steel and concrete, but in comparison to timber. So timber is quite often the, as I said, the default material for low carbon construction. Land use, a tree sits on a 5 by 5 meter square plot. It has a strength of 7.5 newtons, so it's quite a weak material. The tree takes 25 years to grow. So we invented this unit, I can't point anyway, this meter cube newtons per year. So how much material, how strong, how long does it take to produce it? The tree produces 0.336 meter cube newtons per year. The bit of stone under the tree, 500 cubic meters of 150 newton stone that you can remove in 3 months, is 224,000 meter cube newtons per year. So a much more powerful way of getting strong material from a particular plot of land. Quarrying is far more succinct, far more punctual than even in forestry. Somebody else said, oh, you're going to stop building in bricks and concrete and steel, and you're going to build with stone, and we'll have to open up all these quarries. We'll be digging everywhere up. All of those things come from quarries anyway. Concrete comes from a quarry. Bricks come from quarries. So. Stone is much stronger, as I said, in compression. Also much stronger in tension than concrete, which means that you need a lot less secondary reinforcement when you make beams. It's much stiffer. So when concrete sets, it's full of water. When the concrete dries, it shrinks. So if you make a concrete beam with reinforcement in it, it slowly bananas as it dries. And when you compress it, you expel the water that's trapped within it, and then it shrinks even more. So you get these long-term plastic movements with concrete that you don't get with stone. So stone is about 1.5 to 2 times stiffer than concrete. And usually in concrete design, the stiffness is the critical thing. We started designing stone, actually making staircases. We were making wooden staircases based on the principles of a stone cantilever stair. So this is a not very traditional version of a traditional stone cantilever stair. The wires are just there for the balustrade infill. What happens is it's completely unreinforced. One piece of stone sits on the one underneath and carries the one above. It's built into the brick wall on the far side. When you push down here and it's supported here, it has to twist in order to move out of the way, but it can't twist because it's built in the distance, if you see what I mean. So it doesn't really cantilever. It's kind of reciprocating torsional structure. These are everywhere in London and all over Europe, in fact, and it's a rare example of stone being used in tension. So you're using the stone in tension for a structural purpose, which emboldened us to start using stone more in tension. And we thought, yeah, there's a precedent because the staircase is everywhere. Someone else said, oh yeah, what about survivor bias? I was saying, what's survivor bias? And they're saying, oh, the only stone staircases that you're seeing are the ones that didn't fall down. But actually, we were in India. So European historical stone construction has tended to be anti-funicular. And funicular means rope-like. So if you hang a piece of rope, it makes a catenary. If you put it the other way up, it's a perfect arch. Almost all European historical stone structures are arches and vaults and compression structures. They only use stone in compression. But we were doing a project in India recently, and they put us up in a hotel. It was a very old hotel, and you can see that actually in India, the tradition is to build columns and beams and slabs. And so they're building traviated structures where they are using stone in tension quite widely. I haven't been there, but there's a place called Hampi in India that just has the most amazing stone structures where they use it as beams and columns rather than vaults and arches. So kind of an interesting thing. But our stonemasons were frustrated because they could only sell staircases to people where there's a wall next to the flight. They wanted to make free-spanning stone stairs, so we started to experiment with reinforcing the stone. This was an early test. It's 3.2 meter span, 50 millimeter deep stone plates, 2 8-millimeter cables that run with a slight curve. So because of the curve, when you tension the cables, they lift the stone and they push the stones together end on end. So we're able to span in 50 millimeters, 3.2 meters. If that was concrete, it would be 100 millimeters. We took a really bad photo of that prototype. But it's kind of proving the concept that you can reinforce it. We started making short, straight stair flights and then little helical ones. This was our first really big stair. It's 1.4 meters across. It's 270 degrees. Each tread is an individual piece of stone, and there are 2 12-millimeter cables, each carrying 120 kilonewtons of pre-stress. So the cables hold the treads together. You can see on the diagram on the right-hand side, this is the crossette, or it's the intersection between the two stones. This curve means the treads are locked together, so they can't twist against each other, if that makes sense. So we tried this, and it didn't work quite a few times, and we were experimenting with ways of analyzing it, so it's quite difficult to analyze as well. Eventually, we got it working. This is the torture chamber of new staircases. So it's a load test, so all the barrels are full of water to try and prove that that thing would stand up. And this was the first really big stair that we did. There's a really embarrassing balustrade on there now. It isn't on there in this photograph, but it's a really succinct and simple solution, just using the stone to do the structural work, rather than the normal solution, which would be a big thick lump of concrete with stone plastered all over it, which is much thicker, much deeper, much longer to build, a lot more cutting to cover something in a thin veneer of stone than to make solid stones. So quite a great thing, and structurally very surprising. So we spent a long time designing this, and then we went to see it, and it's quite a scary moment. But we've done, I think, now 60 or 70 of these kinds of stairs all over the world. Some of them boring, like the last one. Some of them really crazy, like this one. But we're not really. Well, what's interesting about this is that these are kind of high net worth individuals' houses, so they're spending a lot of money, and they want the staircase to really impress their friends. So if we tell them we're going to take loads of risks and we're going to do loads of R&D, they're happy to pay for it. So we're able to learn a lot about how to design reinforced stone from these projects, even though they're not particularly the projects that we want to be doing. What we really want to do is building, and it was through this process that we started assessing the carbon involved in stone. So I'd kind of always assumed, oh, stone's a luxury product, it's going to be high carbon. When we started looking into it, actually, it's very low carbon, and as I said before. So we thought what we want to do is buildings. I don't know if you know Clerkenwell Close by Amin Taha. So this was going to be a steel frame building and then a brick building, and eventually became a stone building. It's concrete slabs on the inside and a concrete core. So the wind load is carried by the concrete core. There are no other columns within the building. So the stone frame, which is brown in this image, is supporting all of the weight of the concrete. We built the concrete. So if the concrete contractor and the stone contractor were the same person, they would build a slab and they would build the stone, and they would build a slab and they would use the crane, and it would all be one operation, and it would be very, very simple. But because they're two different people and there's only one crane, and because they're both using the crane 100% of the time, they argue about hook time. So you need to separate them in time terms. So what we decided to do was to build the concrete frame and leave in all the back propping, so you can see all the slabs there with no columns in, and then come back and build the stone around the outside afterwards. As you can see, they're single pieces of stone, and there's a kind of cast-in bolted connection in the slab edge there. As a measure to save money, in fact, I think, Amin went to Lyon to look at the quarry, and he found a very traditional stone quarry. It's a Messongis limestone, and what they do in that quarry is drill and plug and feather. So they drill holes, they put feathers, which are like wedge-shaped bits of steel, and they drive plugs in between them, and that forces the stone apart and splits it. When they split it, it rolls off of the bed underneath, so you end up with a split face, and then the bedding plane face. So this has lots of fossils and quite a gnarly finish, and then they sawed them up into the final shape. So there's three distinct finishes on the facade, and he allowed them to arrive randomly on the building. We stood it off from the building because we wanted to make sure nobody thought this was a bit of cladding covering up a steel column. So you can see the stone all the way around. It's completely separated from the building. These wooden shutters open behind the stones so you can get ventilation in without falling out of the window, because the stone column is right there in front. And there's a thermally broken connection up in the top left-hand corner. You can see the steel bracket, and there's a thermal break between that and the concrete slab. The stones get smaller where they have less load. They get smaller near the top. The council wanted to pull it down, which was... I should say, actually, so we're interested in building low-carbon buildings. This is not a low-carbon building. It's got a basement and it's a concrete frame. We took the brickwork away and we put stone up, so So stone is much lower carbon than brick. Brick is really terrible, and we replace the concrete columns with stone. But in totality, this is a pretty average building carbon-wise. But the point is, it shows the prospect that it's possible to use unworked stone as a structural and an architectural finish. If we can do all these things, we can also do very simple things. So what we're quite interested in doing is making ordinary beams, ordinary slabs, and ordinary columns. So you can make a stone beam, blocks of stone, drill a hole, put a cable through, stretch the cable with a hydraulic jack, and wedge it shut. So you literally just string it together like beads on a necklace, and you can make a stone beam. The stone beam has, as I said, about 15 times less carbon than the steel equivalent. It's about the same size, has about the same strength. If I want a steel beam, I need a blast furnace and a rolling mill and all this kind of stuff. If I want a stone beam, I can get a disc cutter, a drill, a bit of cable, and a jack in a suitcase, and I can go to a quarry, and given enough time, I can make a stone beam. So countries, for example, that don't have their own steel industries or have poor balance of payments, this is quite a democratized way of building structures. You know, you don't need a cement plant, you don't need a steel works and that kind of stuff, and very, very low carbon, quite interesting. So we've, this is Wendell, Sebastian in the middle from UCL, and Alex from the stonemasonry company. We have an R&D budget of about £5. And so we've been investing really heavily in making these things. So we do some tests. I mean, we can't afford to do very much. And it's amazing how there are no codes for stone. There are very few examples. Other people have done reinforced stone, but not very many. It's not very well documented. There's no British standard or Eurocode for reinforced stone, so we have to kind of make it all up. And it's incredible at the beginning of something how a tiny bit of investigation tells you a lot, but also suggests a multitude of other questions. So we're constantly finding things that we don't know and trying to find ways of solving them. We were worried about fire. So we can design the beam. If we burn limestone, we'll get cement. 700 degrees limestone turns into cement. A fire in a building is supposed to be 1,000 degrees. So we're worried if we have a limestone building and there's a fire, it's going to turn into a nice, neat pile of cement afterwards. So this is a fire test. It's a 7-meter beam carrying 2 10-ton loads. Actually, because concrete contains water in the way that I described before, when the water turns to steam, it builds up a lot of pressure within the concrete and it explosively spalls the face of the concrete, exposing the reinforcement, and so the reinforcement melts and the steel falls down. Limestone didn't behave in the same way, so we've got a 3-hour fire resistance from this beam, which is quite surprising and pretty good. We made a.
Can I just ask you, because you keep saying stone, but is it mainly limestone?
We can do this with any stone. We've tended to use limestone because well, A, it's easier to work, and the stonemasons that we work with are limestone stonemasons, but actually we want to use other stones, stronger stones. So limestone isn't necessarily the best stone to use, it's just the one that's been most available. So again, this is a limestone. We were asking, or we were looking at commercial buildings. How would you use stone in a commercial building? People want office floor plates with 12-meter spans for I don't know what reason. Roller skating around the office. I don't know why they want 12-meter spans. Column-free spaces are really the enemy of sustainability. Trying to make Heathrow Terminal 5, that roof, what is it, 120-meter span, and you go in there and there are little bollards with tapes in between. They're like, oh, we're going to justify 7 zillion tons of steel to have a column-free space, and then you have to walk everywhere, snaking around. It's just complete lunacy. They could have had columns all over the place and nobody would have noticed. But anyway, that's where it is. This is a 12-meter span. It's a 450 mil by 200 mil beam. It's connected to the floor plate on top, and the two things act compositely. So you can see this castellation in the side of the beam is grabbing the floor plates on top. So when it bends, it compresses the top. And yeah, that's designed for a full office load. Incredibly simple to make, not a huge investment, and very structurally effective. We did another one in the Royal Academy Summer Show, and here we're using granite, which is recovered from a demolished building on the ends. So where the stresses are really high at the anchorages, and in the middle we're using granite, and in between we're using a slightly weaker limestone from Portland. It's Portland roach bed. Most quarries are extracting stone for aesthetic purposes, and probably only 20% of what they extract is sold. and the rest is crushed up for aggregate or just left lying around outside the quarries. So the carbon footprints I'm stating are based on the 20%, 80% relationship. If we're building a structure, we don't care what color the stone is particularly. So we can start to use all of that unwanted stone, and the roach bed was given to us for free because it looks like old concrete and they can't sell it to anybody. So that's, and you can reuse stone from previous buildings. But here we've got a 200 millimeter deep beam cantilevering 5.5 meters from the timber frame. We won the award, the Architectural Room Award for this, which is quite nice. And we're sort of suggesting this T-beam like a concrete beam, because people are used to seeing concrete beams, so sort of intentionally evoking that this is a bit like reinforced concrete. And also the fact that the stone beam is light enough to be supported by a timber frame, or conversely, the timber frame is strong enough to support a stone beam, that actually it's a slight perversion of the order that you would normally see those materials in. We've built lots of projects with stone beams. The biggest project at the moment is a £75 million house out in Oxfordshire, where we have load-bearing stone. Again, it's an Amin Taha building, load-bearing stone walls, and post-tension stone slabs. So all of these elements are structural stone beams and quite big span stone slabs. That's the beam factory. So you can see how little investment is required to make this work. So, you know, the government would rather build a nuclear power station to decarbonize and continue to build in brick and concrete and steel. Actually much easier to make timber and stone components, not that much investment to decarbonize construction rather than solve the problem with nuclear power. Stone slabs, and that's a 10-meter stone slab within that building, so spanning from here to the far side. On that, another project, we were kind of, so part of this is making very simple traviated forms, very simple stone beams, but also there's a question about form, and particularly with underground structures. But we were kind of experimenting with the students. Funicular structures, things that hang upside down, also stand up in compression. So you can do these amazing experiments with plaster of Paris, and what you hang upside down is obviously going to be mathematically perfect as a compression structure the other way up. So we're able to kind of find these fun and interesting shapes. If you choose the right shape for something, it will be far more efficient. And in the case of the project I'm going to show now, it's a basement. The normal way of building a basement is a rectangular box. But everyone who built any kind of engineering structure underground, it's round. Tube tunnels around, sewers around, wells around. You know, earth pressures act circumferentially, and earth pressure mitigates against buckling, so you can have very thin compression structures for round structures. If you put an egg underground, it'll be fine. If you put a shoebox underground, it'll be crushed. So when we build rectangular underground pool boxes, they're all 600 millimeters thick, very, very heavy reinforced structures. So we were interested in finding other ways of doing that, and potentially with stone. Hanging ropes upside down is the inversion of gravity. Inflating something like that is the inversion of soil pressure acting inwards. So it's a kind of reversal of pressure. So we're finding a form for a strapped vault that we used in this case to build this, this underground swimming pool. So the sheet piling goes in around the perimeter to make the hole. The thing is built in that shape, 100 millimeters of stone and some reinforced ribs. It's buried, and then the sheet piling is removed afterwards. So a far more efficient structure and a more interesting one, although maybe a little too architectural, I have to say. So the other thing we were interested in was, this is Mallorca. Ibavi are a housing collective in Mallorca, and traditional building in Mallorca is with stone, because the whole island is stone, and the stone, you know, you dig 1 foot under the ground, there's stone absolutely everywhere. And they were tending to build in concrete, but they wanted to decarbonize the way they built social housing, so they built a lot of solid stone, you know, very recently, a lot of solid stone social housing units using the local morass sandstone. And the guy there is saying, there are 7,000 spoken languages in the world, all responding to their local environments. Why aren't there 7,000 architectural languages? And I was thinking this kind of interesting question. So when we're building here, our stock decarbonization solution is CLT. So we're importing CLT from Switzerland, Austria, Finland, whatever, places where there's a lot of trees. So CLT is very thick, very heavy timber construction, and it comes from a place where there's a lot of wood. We don't have the kind of quarries that Mallorca has or the quarrying industry that France has. We don't have loads of stone either. And we were sort of joking around, there's the potato-tomato line across Europe. So everyone below the line is eating tomatoes, and everyone above the line is eating potatoes. It's probably also the stone timber line, and the Protestant Catholic line, and the hot-cold line, and all kinds of other things that sort of divide Europe north and south. And as usual, the UK is floating around somewhere in the middle, not really quite sure what it is. So here, we've been working on a series of buildings where we do the MEP, we do the air conditioning design and structural design. If we can make the building heavy with exposed finishes, we don't need air conditioning because the UK is not quite hot, not quite cold. And so if we have exposed stone or concrete in the soffits of the building, we don't need air conditioning. But if we make the building a massive concrete slab, then we splurge all the energy that we save from the air conditioning on the structural frame, which is completely pointless. So we came up across several projects with the idea of building timber frames with very thin concrete soffits. So we have just enough mass in the ceiling to remove the air conditioning, but enough for it still to be a timber frame. So that's one of a series of 6 or 7 buildings that has that solution. And in this case, it's a Baubucher timber frame, so it's LVL beech, laminated beech beams, 75 millimeter concrete slabs connected compositely to the timber. So we're bolting the two things together and leaving it exposed in the soffit. So the whole of the inside of the building looks like this. We have no air conditioning. The windows are actuated, so they open at night and the concrete cools down, and they close in the daytime, and the concrete absorbs the heat from the office. But obviously the concrete has quite high carbon. What can we do about that? So we were thinking after that, we'll look at removing the concrete from that solution and replacing it with stone. So we still do little projects, loft conversions and back extensions and things like that. So if we have an idea, we find a victim with a back extension and we put it in, that one and see how it goes. So this is somebody's house in Primrose Hill. It's a Georgian house. We have a big, again, I can't point, a big timber beam across the back of the house supported on stone columns. We have a post-tension beam spanning across the back of the extension, and then we have timber joists and stone plates acting compositely spanning between the house and the stone beam. So that's the post-tension stone beam on a timber post on that side, and that's what the soffit looks like both on the inside and the outside. So it's limestone and Accoya, and I think this, in terms of what's good for us here in the UK, not quite hot, not quite cold, not quite timber, not quite stone, sort of lightweight. This is, I think, a good vernacular for us because we use the timber that we've got, we use the small pieces of stone that we've got. It looks great, and actually you can span a long way with a post-tension stone beam, and you can infill with the timber and stone. You can get rid of the air conditioning. It's got decent fire resistance, better acoustics. So I think this is an interesting thing, and we've built a whole series of buildings now using, and every time a slightly bigger one, using those ideas. We were interested, in using stone, as I said, using stone in flexure is quite a scary thing to do because the flexural strength of the stone isn't that difficult to assess. But if you've ever seen a tile puzzle, sort of Mickey Mouse, slide the tiles around, the tiles don't fall out, and there are no rails on the back of the puzzle. And actually what happens is that the tiles are torsionally locked. And so here we're making essentially a stone tile puzzle. It's supported on the edges on these steel stalks. It spans across the middle 3 meters. Each tile is 500 millimeters square. These are diamond-shaped washers above and below the stone with a bolt that passes in between that stops the stones from moving relative to each other. The way this works, the cornerstone is supported on 3 points, and so the 4th point is stable. You can build the next stone next to it with the 2 supports there fixed onto the previous stone, and another one here fixed onto the previous stone, and then you can build that one. So you can build this reciprocating stone structure spanning 3 meters, 50 millimeters thick without any reinforcement or post-tensioning at all. It carries a domestic load at 50 mil. And actually, it's quite redundant. You can break, rather like the tile puzzle, having the missing tile all over the place without falling out, you can break any number of the stones before it actually collapses. So I'm thinking this is quite incredible. We did a stress analysis of this stone, and the result was 4 love hearts. Like pattern of stresses. If you do a stress analysis, you get a kind of heat map of where the stresses are, and the results were these 4 red love hearts in the middle of the slab. So we thought we were onto something. As in the Aronofsky film Pi, where he's discovering the number of God, we were thinking there's a message in this slab, God's own logo, perfect stone slab. So we're thinking there's a system we can make out of all of these pieces. So rather than having the washes that you can see, we put a cruciform in between the plates, post-tension beams, post-tension columns, deliver it as a kit. So someone said, oh, that's all very well. What about the logistics? Somebody who's advocating concrete is talking about the logistics of this. So you would think delivering a liquid material on a truck with a revolving tanker on the back that goes hard after an hour and a half is good logistics compared to delivering upcyclable, standardized stone components on the back of a truck. So there's so much inertia with the way things are done now. People really can't see anything else. We made a prototype of that. So this could be a really quick, low-carbon way to build for other buildings. But we don't know. When they built Iron Bridge in Telford, it was the first, maybe not the first, but probably the first significant cast iron structure. And all they built to date was wooden structures. So they didn't really understand anything about cast iron or steel as a material. No, they didn't understand. It just hadn't been invented. So all of the detailing on that bridge is mortise and tenon joints with wedges. So that you can see that the people who designed it, they had timber in their heads. They didn't know, they couldn't see any other material. And so they're using wrought iron as if it's timber. When they first started using concrete, LA is full of neo-Gothic concrete churches. The Empire exhibition in Wembley was all neoclassical concrete. And they thought concrete was a new stone. And so the typology of the first concrete buildings were all kind of these heavy neo-concrete or neoclassical buildings. Until the Bauhaus came along and started, reinventing the way that concrete was used. So when we're designing these stone things, we're rather fixated with concrete and timber and steel. We don't really know what the typology of stone might really be. So partly what we're showing is things that are analogous to concrete. Here we're thinking actually maybe it's more analogous to steel. So we make stone stick beams, and we have bolted connections, and we erect it as if it's a steel frame. Eventually stone will have its own typology, probably coming from factories and industrial processes rather than designers, or the pragmatics of construction, and it'll be something completely different. We don't know what it is yet. Yeah, we were joking that you can build your future dystopia with stone. Stone's a lot more powerful than timber. It's much, much stronger. You can get gabbros and granites with strengths of 300 or 400 newtons, like steel. So you can build really high, really impressive buildings, but with far less carbon. Actually, this image is Blade Runner, which was made in 1982. And the opening shot is LA 2019, which is kind of, we're thinking that, if you're in 1982, you grew up on a horse cart and you saw people land on the moon. So extrapolating from that, you probably saw flying cars and huge cities and whatever. And we have the same shit they had in 1982 plus iPhones. But anyway, maybe that's the future we can...
Would you take some questions, Steve?
Yes, yeah, absolutely.
Steve, thanks for the talk.
Hello.
So really good. We keep going on to students that technical drawings don't look a certain way, and I think you've shown your technical drawings, and that's the kind of thing we want from the students.
Oh, the sketching.
Yeah. I mean, they're completely technical, aren't they?
Everyone in our office gets sent to sketching boot camp. And if they do a bad sketch, we screw it up and make them do it again, which we call training and they call bullying.
I just wanted to ask I thought you said that the house in Oxford was, how much was it? 72?
75 million.
75 million. But that's not a private house, is it?
It is.
Is it? Yeah.
Yeah. Yeah. It's a lot. Yeah.
Yeah. But I suppose that brings us around to the point that you've been quite open about the fact that you go for these top-end, often private residential projects, and because that's your R&D,
Yeah.
you get paid a fee, which they can pay, and
Yeah.
actually you're able to do your research and experimentation kind of under the radar. The client, I don't know, they may be aware of what they're getting, or they may not, but
Yeah.
it's...
I mean, stairs were always, so we do sometimes bridges, and we used to do a lot of staircases. And when I started working in the 90s, you know, every office building was a bit high tech and had a really fancy staircase. So we designed the boring metal frame and really looked forward to the staircase. And bridges are so painful. It's like 5% design, 95% checking with the local authority. You know, it's really, whereas staircases, you know, they're all structure and you can do whatever you want and nobody even reads the calculations. So you can really go a lot further with staircases than with other things. And I think, yeah, there's a huge level of inequality, the amount of money that high-end, you know, 3 stories. Somebody told me once in Westbourne Grove, oh yes, we're having a lot of trouble on this job, and we need you to come in and help us, and we're doing 3 stories with a cinema and a swimming pool, but we're on a budget, don't make your fee too much. And I'm like, I've just come down to Westbourne Grove from Willesden on my bike, and you're telling me you are on a budget. So, yeah, I mean, I think I think it's nice for me, it's nice for our employees that the work we do, as well as being kind of technically interesting and creative, also has some kind of social mission, right? I'm sure that, you know, in a few years' time, everyone will say, well, that was a stupid idea and you were completely wrong-headed, but at least, you know, we try and do something. And so I think, and we don't choose those jobs, actually. We're like every other practitioner, we're desperate for all the work we can get. So when they arrive, we take them. And, but we try and make, I mean, I think having worked, when I worked for Calatrava, we were doing all sorts of crazy buildings, and then coming back here and doing back extensions was, you know, you want to eke out of every project as much technical interest as you possibly can and really try and push it, because otherwise you'll just be bored to death. But I think it's, you know, pretty architecture is great, but engineering has depth. You know, it's like it's got reason and science and calculation. You know, it's not just what it looks like. There's a lot behind it, and I find that very satisfying. Sorry. Having said that, I'm going to run now.
I just want to ask about where the stone comes from. I just want to ask where the stone comes from and about the costs.
So we sometimes use UK stone. The thing in the which way is this going? The thing in the RA was Portland. There's the RA thing. So that's Portland. The granite came from a building that was demolished in the UK. There isn't in France after the Second World War. They, as I said before, had a shortage of coal, and so they had what they called austerity construction. And they realized that it took 200 kilograms of coal to make a meter cube of concrete, but only 5 kilograms of coal to make a meter cube of stone. So they gave a lot of money to quarries, and there was a guy called, I think, Paul Massaroux, who developed a stone cutting machine that would cut a standard module of stone. Oh, and actually the quarry that I showed on the photo with the tree is down there as well. And they built, Fernand Pouillon, the French architect who's rebuilding Marseille and building buildings in Algiers, was building in those standard stone blocks. And so the French quarrying industry is far more, as a consequence of that, it's far bigger. I think they have a lot more space, they have less NIMBYism, and they have a more industrialized quarrying practice, whereas here, stone can be quite expensive. There's another, so we tend to use a lot of French limestone. We use some stone from the UK whenever we can. There's a quarry in that do kitchen worktops in Larvik in Norway, in the south of Norway, and they're right next to a port. And they sell, as I said, 20% for kitchen worktops, and they have a lot of stone there left over that they use to build motorway embankments and stuff like that. So they're looking for places to use big lumps of this incredibly homogeneous, quite strong granite. And they tip it into a shipping container, and it goes straight onto a ship, and then it arrives here with quite low embodied carbon because of the transport, because shipping is much better than road transport. But there is nothing to stop people opening quarries here. There's loads of stone under the UK. We just don't currently do it very much.
And what about chalk?
Oh, do you know, what is it? Lutchen's Marsh Wall, isn't it? And Woburn Abbey. There's a quarry near Luton where they make clunch, or they dig up clunch. And the guy said he's following Roman chalk mines with his digger. He goes up there in the summer because there's no water, and he cuts it up and he sells it. And, so I'm asking him, how much per meter cubed? And he's going, per what? Cubic yard. It's quite a duffel coat. Such a cottage industry, very difficult to buy that stone and use it on any kind of serious project. And also clunch is very, very soluble, but I mean, it's beautiful as a stone. If you make it bigger, then, sorry.
Yeah, sure.
Thanks for your lecture. There's also interesting parallel to this, and you mentioned Armin Taha, and he is a huge advocate for reusing the stone that isn't used as a cladding material for rain screens in making stone bricks. And I was addicted to this aspect, and I wanted to try and convince a practice I worked at previously to swap out the use of fired high carbon bricks with stone bricks. But then, of course, you need to account for the weight of each stone brick and how that then contributes to how much foundations you need. And you mentioned how stone can be lighter than concrete, but then in comparison to timber, timber is far lighter, so it would need less concrete foundations.
Yeah.
There's also there's a comparison between the formwork for buildings versus its foundations in carbon.
Yeah, okay, so there are a lot of questions in that. Yeah, I mean, so bricks are bricks because a malnourished, sickly Victorian bricklayer could lift up a 1.5 pound brick and slap it into a piece of mortar one after another. They could lift a hod on a scaffolding without being crushed under the weight. That's why a brick is the size that it is. It's become completely stuck in our culture. So they would build 8-inch brick walls, which were strong enough to carry the floors of a building and strong enough to resist wind loads at 8 inches thick. With lime mortar, so they're flexible and they can move with brick expansion without cracking. So then somebody has the genius idea of making cavity walls, which are half the strength, so now you need wind posts everywhere. They put cement mortar in that can't resist any movement at all without cracking. They put block work on the inside which shrinks while the brick is expanding, so you've got to put mastic vertical joints. The thing isn't strong enough to carry the floors, so the floors have to carry the walls, which is the most ridiculous thing in building terms you've ever heard. And people continue to build, and not only that, but 240 billion bricks used in the UK every year is about half the output of a nuclear power station in carbon terms. So do you want a nuclear power station or do you want to ban bricks? Well,
but it's vernacular now.
Nuclear power, that's the way ahead. You know, but Amin is saying it's such a cultural shift to move people away from brickwork. They're so addicted to bricks in cultural terms that you say, okay, we'll make the brick out of stone. Oh, okay, yeah, I understand that. Yeah, we'll do that. But actually, the brick doesn't weigh, the stone brick weighs hardly anything more than the clay brick. Actually, they're similar weights. Brick doesn't expand in the way that clay ceramic products do, so you don't need so many movement joints. It's much stronger in other respects, so it's quite a good substitute for the brick. But the question is, why are you still persisting with this archaic, like 1850s or 1800s construction material? So I went to a place and they said, oh, look at our new stone bricks, and it's amazing. So they have a big slab of stone, 1 meter square, 100 millimeters thick, and it's like, you think, that's a really good slab of stone. We cut it up into these little bricks so it can be shipped to site, put back together again. You think that's total nonsense. Did you go to the Design Museum?
I went to Clark Design Week when he was.
Oh, okay. Well, the Design Museum has a little show, but you can get 1 meter square, 50 millimeter thick stone planks. You can make a wall. Where is that? The funny floor thing we were making. can be a wall really easily. Sorry, we'll flick through a lot of stuff to get there. Yeah, I mean, that can be a wall. So you can make a wall that can carry wind load, can carry vertical load, doesn't need bed joint reinforcement or wind posts, and can be 50 millimeters thick. But a bricklayer can't lift one at a time, so you'd have to have some kind of little assistant crane or something to do it. But, bricks are nonsensical from the get-go. Stone bricks are better than clay bricks, but it's still nonsense.
And what about the shortage of skilled labor when you have a huge industry of bricklayers and brick production? I've seen our entire building is
in pharaonic times, we had a huge supply of labourers who could drag rocks up ramps. We're like, oh, well, we can't move away from that because we've got lots of skilled slaves who can drag rocks up hills. Of course, people have got to change. And, brickwork is yeah.
With something like that big house you're doing, how do you deal with the insulation? I mean, what is the wall build-up, and how does it deal with cold bridging and things?
Yeah, we have 2 layers of stone with the insulation in between, so the cavity wall.
So there's 2 load-bearing stone walls?
Internal load-bearing stone wall, thinner layer of stone on the outside as a cladding material.
Okay.
So it's still a cavity wall construction. I think below a certain tomato-potato line-ish point, you probably don't need insulation, a 300 millimeter thick. So Gilles Péradin and Pouillon, all these people in the south of France are building solid stone walls. And because the annual temperature average is close to what you want on the inside of the house, the thickness of the stone stops the cold snaps from affecting the internal environment. So you don't need to insulate.
But in England, you've got to
yeah, in England you have to insulate.
separate.
Yeah.
Mm-hmm.
Yeah. I mean,
Lots of people live in stone buildings. Not lots,
yeah.
but people do live in stone.
Well, millions of people live in Victorian houses with solid 8-inch walls without any insulation. I mean, it's not great, but it's certainly possible. Yeah.
Look, thanks so much, Steve. I've just got one quick question myself, which is you don't really talk much about the steel cabling. I mean, maybe it's just so straightforward; it's just not really much of an issue. But is that complicated? Complicated gear to post-tension it, or
No, it's very. Yeah, I was trying to find the beam factory shot. Yeah, so that's the strand, and that thing sticking out the end is the loading bridge. So you thread it through the hole. A post-tensioning jack is just like a bicycle pump, slightly industrial version of a bicycle pump. You have a kind of hand brake crank box with a oil reserve in it. It's tiny and really cheap. And you pull, so we probably extend the jack by about 25 millimeters on those things and stretch the cable out. And then we use a barrel and tapered wedges that just clamp the cable in the end. It's incredibly simple. And it uses, I mean, the advantage is that so in a steel I-beam, most of the steel is there for deflection. So you're trying to stop the beam from being too bouncy. So a lot of the steel is there for deflection. Some of it's there for stability, because when you stress a steel I-beam, it wants to flip out of the way. So that's why you have the flanges to stop the beam from torsionally buckling. Very little of the steel is there for strength, but steel is steel is an amazing material, and it's an incredible material and really easy and solves loads of problems incredibly powerfully.
You're using its properties, basically.
Yeah, so here we're using it because we're stretching it into the maximum tension it can take and clamping the stone together. The deflection, the stability, all the other things are dealt with by the stone in compression, and only the tensile strength is being used for the steel. So we have much less steel than would be in an equivalent I section. That makes sense.
And you can achieve 200k newtons with a small piece of apparatus for the tension.
Yeah, easy. Yeah, yeah. Wow. Oh, you can get much more.
200 tons.
20 tons. Yeah, yeah, yeah. Yeah, probably. I don't know what jack capacity. We've never had anyone complain about the jack capacity. It's always the something else that happens. But yeah, it's really very simple, very tiny bits of plant, and compared to other. Yeah.
Sorry, you might have answered that question already in your talk, but do you need to check every stone according, because it's individual pieces? Do you need to check its strength?
We take, so we take a series of, yes, I mean, I think, as I said, there are so many things that we don't understand. There are lots of different kinds of stone, and we don't know that much about just being structural engineers, we don't know that much about the chemistry of stone or the petrography or the things that that affect the stone's strength. So we were always thinking as they dig a quarry, a bench moves forward. So we're thinking if we take samples here and we work out the strength of the stone, we wait for a few months before we take samples again, assuming that there's a kind of lateral variation on the stone. But actually, all the layers in the limestone, probably the weather in whatever Jurassic environment changes the strength of the stone vertically rather than horizontally. So maybe we're going to actually want to take samples vertically. So what we do is take random samples, 10 or 15, break them, take an average, take 2 standard deviations, and then put a really big factor of safety of 3 on that. So we have a really, really big factor of safety on all the stone because because it's a natural material and it's unpredictable. If there's a future for stone, it will be somebody far more intelligent than me who works out how to X-ray it or ultrasound it or some other assessment that will tell them how strong the stone is. So when they make glulam, they electrograde the glulam and they put the strong timbers in the top of the beam and then put the weak timbers in the middle. And so that kind of thing would be amazing. But at the moment, we take a few samples, we take an average, we put a big margin on it, and we stick a huge factor of safety on it because it's a bit scary.
And just to your insulting comment about architects
Oh, yeah.
being irrational.
I don't think you should take that as an insult.
Yeah, well, or maybe, that's what it's supposed to be, but obviously, engineering is much more deep and clever, but if humans would be deep and clever and rational, we wouldn't need architects.
Look, thanks, Steve. That's fantastic job. Thank you. Thanks very much. Thank you.